Good afternoon. I am Mohammad Tariq Haibullah from Bangladesh University of Engineering and Technology, Dhaka, Bangladesh. Now I am going to give a presentation on our conference paper titled Non-Ballistic Conduction in Bundle of Single-Wall Carbon Nanotubes with Disorder. We know carbon nanotube has become a topic of extensive research because of its some extraordinary properties. It was first invented by ICECE in 1991. It can be semiconducting or metallic. And the upper figure represents 77 centi, which is a metallic, and the lower figure is a 130 centi, and it is a semiconducting. Its electrical, optical, and thermal properties can be tuned. Besides, CNT possesses better electrical properties such as higher electrical conductance, which is close to copper, and longer mean-free path, which is in the micrometer range. It also has a quantized conductance. So this is why we have focused on conduction in carbon nanotubes in our work. Carbon nanotubes can be applied in various fields and areas like energy storage device, biomedical, air and water filtration, interconnect, atomic force microscope, and CNT-TFT or carbon nanotubes thin film transistor. Here the left figure represents an fabricated IC in which CNTs are used as interconnect, and this CNT interconnects connect the two metal layers. The the right figure represents CNT-TFT, in which CNTs are used as channel materials between source and drain of the transistor. We know the conduction in a single-wall carbon nanotubes can be greatly affected by disorder. The disorder reduces mean free path of carbon nanotubes, and this results in reduced conductance of the CNT. In this figure, in this figure, with the increase of disorder strength, the quantum conductance of a CNT is reduced. So we have studied the disorder effect on a single wall carbon nanotube bundles in our work. These are the structures which were used in our work. The upper figure represents a 0.8 nanometer diameter CNTs, and the lower figure represents 1 nanometer diameter CNTs. This is 66 CNT, and it is metallic, and this is a 75 CNT, which is a semiconducting. This is 77 centi, and it is metallic, and this is a 130 centi, and it is semiconducting. This is the computational procedures for calculations of 0.8 nanometer diameters single wall carbon nanotubes. For the calculations, at first we have collected density of states data from website. Then from the data we have identified band of singularities, and from the singularities we have performed ballistic conductance calculation. Then at the end we have calculated non-ballistic conductance for these types of CNTs. But for 1 nanometer diameter CNTs, the computational procedures are different. For the calculations, we have used quantum espresso and MATLAB softwares. At first, we have optimized all the atoms in the unit cell of this type of CNTs. Then we have minimized through these optimization procedures, we have minimized the total energy of the system, and that this step this step was performed using quantum spacer software. Using the same software, we have performed SCF and SCF calculation, DOS calculation, band structure calculation, and ballistic conductance calculation. At the end, we have a calculated non-ballistic conductance of this type of CNTs with the help of MATLAB software. We know Next, we proceed to the theory which was used in our work. We know ballistic conduction is such kind of conduction in which a mean free path is greater than the length of conductor or length of carbon nanotubes. This is the formula for current due to ballistic conduction. And if when a voltage is applied across a CNT, there is an imbalance created between the electrochemical potentials of the two electrodes, left electrode and right electrode. And due to this created imbalance, the current flow is initiated through the CNT. This is the formula for ballistic conductance of CNT. Uh, and the ballistic conductance is quantized and depends on NC or number of quantum channel. But for non-ballistic conduction, mean free path is less than the length of tube or CNT, so electrons face collisions while flowing through the CNT. For non-ballistic conductance, this is the formula for non-ballistic conductance, and which depends on the mean free path of carbon nanotube and length of CNT. The mean free path of CNT also depends on disorder strength W and this square root term, and this square root term represents the diameter of CNT. These are the calculated electronic band structures for 77 CNT and 130 CNT. As 130 CNT is semiconducting, there is a band gap between valence band and conduction band. These are the calculated values of DOS and conductance for 77 CNT. As for 77 CNT, there is a there is non-zero value of DOS and quantum conductance at Fermi level because 77 CNT is metallic. Again, in the right figure, the blue lines represent the conductance of 77 CNT for the length of 1 micrometer, and the red lines for the length of 5 micrometer. So with the increase of length at the same disorder strength value, the quantum conductance of the CNT is reduced. Again, within the same value of length, with the increase of disorder strength, the quantum conductance is decreased. These are the calculated values of DOS and conductance for 130 CNT. As 130 CNT is semiconducting, so the value of DOS and quantum conductance at Fermi level is 0. These are the calculated values of DOS and conductance for 66 and 75 CNTs. This is the table which displays scaling factor and mean free path values. For a 66 CNT, the diameter is 0.8 nanometer. So for a 66 CNT, with the increase of disorder strength, the mean free path value of the CNT is reduced. So conductance of the 66 CNT is also reduced with the increase of disorder strength. Again, at the same disorder strength value, with the increase of length, the scaling factor is reduced. So conductance of 66 CNT is also reduced with the length of CNT at same disorder strength value. Again, for 66 and 75 CNTs, the diameters are same, almost same. So at same disorder strength values, the mean free path values of these two CNTs are almost same and comparable to each other. But for 75 and 130 CNTs, the diameters are different. So at the same disorder strength values, the mean free path value of 75 CNT is less than that of 130 CNT. Again, 75 CNT diameter is less than 130 CNT diameter. So this indicates that the with the in, this indicates that with the increase of diameter, the mean free path value of CNT is increased. These also indicates that the conductance of CNT is increased with the increasing diameter of CNT. This is the table which shows the effect of Fermi level shift. At 0 electron volt Fermi level, the quantum conductance is minimum. But if we shift Fermi level to -1 electron volt and +1 or +1 electron volt, the quantum conductance is increased. So through through Fermi level shift, the quantum conductance can be enhanced, and the Fermi level shifting can be done through N or P type doping. Here are the conclusions of our work. The disorder strength reduces mean free path and also conductance of CNT. And for CNTs at fixed at same diameter and disorder strength value, the conductance is reduced with the length increase, and this can be represented by this figure. And at end, the conductance increases with diameter, while other parameters like length and disorder strength are constant. Again, a Fermi level shifting also results in enhanced conductance or quantum channel. So this is the presentation of our work. Thanks everyone to listen to my presentation. If you have any question, feel free to ask me. Thank you.